Well, hello, ladies and gentlemen. We're going to continue on with our discussion of properties of pure substances. So today's topic, we're going to round off quality by illustrating the geometric or graphical interpretation of quality, X. So we introduced quality last time, which is the mass fraction of the saturated vapor in the mixture. So we're going to talk about how to interpret that on a TV plot. And then we're going to look at how to calculate properties for supercooled liquids and superheated vapor. We've already talked about how to calculate properties for mixtures, saturated mixtures, using quality. So we're going to move on to supercooled liquids and superheated vapors, okay? And as you might guess, these calculations involve using the tables out of your textbook or your notes. So you need to procure a copy of the textbook or your notes here pretty soon so that you can start doing the homework due next week, okay? Okay, so geometric interpretation of quality. So let's move on to show you how to represent quality in terms of the saturation dome. So we have temperature and let's say specific volume. Let's do the TV plot. And here's our saturation dome right there. So let's say we're on a particular isobar. So here is our isobar. So P right here. So we have some sort of a container filled with saturated liquid and saturated vapor at some pressure P and at some temperature T, let's say, okay? So we're somewhere on the isobar, P isobar. Let's say that our system here, our mixture is at that state on the isobar. So it's a saturated mixture. And of course, let's put in some relevant isocores here. Isocore means constant specific volume or constant volume. So we have specific volume for the saturated mix. That's that right there. And then we have specific volume for the saturated liquid. That's the specific volume for the saturated liquid on the left-hand side of the dome. And on the right-hand side of the dome, we have specific volume for the saturated vapor. Now, quality, we had an equation a little while ago. Quality can be calculated in terms of specific volume as a specific volume of the saturated mix minus the specific volume of the saturated liquid divided by the difference in specific volume of the saturated vapor and the saturated liquid. Saturated liquid. I'm getting lazy. I don't want to write all that stuff out. Now let's look at how that equation there can actually be represented on the TV plot. So the numerator, which is VSAT mix minus VSAT liquid, that represents this length right here. Okay, VSAT mix minus VSAT liquid. So that represents the sort of green here. So this represents the green line. I guess that's green. Okay, that's the numerator. And then VSAT vapor minus VSAT liquid in the denominator, that's represented by this yellow line, or this yellow distance right here, okay? So, in the denominator, we have the yellow line, and the numerator, we have the green line, or length, or segment, if you like, okay? This distance divided by this distance, take the ratio of the two and you get the quality, okay? So that's a geometric interpretation of quality. By the way, let's just make sure this makes sense. When quality, let's see here, when the specific volume is when we have a saturated liquid, if we have a saturated liquid, that means we're over here on the left side of the dome. That means V mix is equal to V sat liquid. We're all liquid. And that means that this green distance goes to 0, goes down to 0, okay? And that implies quality equals 0 over the yellow line, or 0. All saturated liquid. All saturated liquid. Okay? So if X equals 0, it means we have no vapor. It's all saturated liquid. Okay? Likewise, if we have a saturated vapor, we switch the screen here. If we have a saturated vapor, I guess I better stick with the other side. Kind of going to go back and forth here. If we have a saturated vapor, and that means we're over here for a saturated vapor. So this green line is actually the entire length, which is the same as our yellow line. So for saturated vapor, the green and the yellow line are of the same length. So saturated vapor green equals yellow equals, not implies. The green and the yellow are of the same length, and so that means X, which is your green over your yellow, is equal to 1. Okay? So when X is equal to 1, we have a saturated vapor. Saturated vapor. No liquid. Okay? So geometric interpretation for quality. The distance from the saturated liquid to the actual state of the mixture on the TV plot divided by the difference or the distance between saturated vapor and saturated liquid on the TV plot. That ratio gives you the quality. It's a geometric interpretation for quality. When you're a saturated liquid, the green arrow shrinks to 0. Saturated liquid, this distance shrinks to 0, and you get X equals 0, or quality equals 0. And when you have a saturated vapor, over here, the green arrow is as long as the yellow arrow, and you get a quality of 1. So that's the geometric or graphical interpretation for quality, okay? And by the way, this goes for specific volume, or I can do specific internal energy. I could put a U here, or I could put an H, enthalpy, specific enthalpy. So this works in general. This is a general interpretation, graphical interpretation of quality. I could put TV, TU, or TH here. Or, for later on, TS. S will be entropy. We'll deal with that in a month or two, okay? So this is a general geometric interpretation, all right? Tell you what, why don't you box this up? This is an important equation. just to give you an idea of how to interpret graphically the quality. So I put a little box around it. Okay? Okay, let's move on to properties of supercooled liquids. Properties of supercooled liquids. We now know how to get properties in the saturated mixture region, in other words, inside the dome. How do we get properties to the left and to the right of the dome? All right, so properties of supercooled liquid. Now, let me show you again. Let's put up a TV plot. I could do PV, but I think TV is just fine. So here's our saturation dome. I'm going to be a bit more accurate drawing the saturation dome. I've been a little bit crazy. I'm just making it a hump. In reality, the saturation dome is very steep on the supercooled liquids, on the saturated liquid side, and very shallow on the on the saturated vapor side. So here we have the critical point. So in reality, the left-hand side or the saturated liquid side of the dome is almost vertical, And that means that the isobars get very steep as we approach the dome. So here are a bunch of isobars. I'm not going to draw them all. But I'll draw a few of them. A bunch of isobars here, okay? They get very steep. The whole side of the curve is very steep. And this is true for not only specific volume, but specific internal energy, okay? Yeah? Now, what this means is the following. Given that it's so steep on the left, so saturated liquid side of dome, almost vertical. What that means is specific volume and specific internal energy don't change much with temperature. Okay, they don't change much with pressure, and they don't change much with temperature either. So because it's so steep here, and these isobars get so close to vertical, what we can say is that the change in specific volume with respect to pressure, okay, is much less than the change in specific volume with respect to temperature. Okay? And also, because these isobars are so steep as we approach the curve, because this is true, we can therefore say that specific volume evaluated at any temperature or pressure for a supercooled liquid. So if I want to calculate specific volume on any isobar for any temperature in the supercooled liquid region, that means out here, the specific volume for a supercooled liquid at any temperature and pressure is approximately equal to the specific volume of a saturated liquid at temperature T. So instead of having separate tables, supercooled liquid tables to look up specific volume of H2O for any pressure or temperature in this region. So over here we have supercooled liquid. So instead of having tables here and having to look up for a temperature and a pressure the specific volume of a supercooled liquid, all we got to do is find the specific volume of the saturated liquid at the temperature T, okay? So I would put a little box around this, okay? Specific volume of a supercooled liquid, in other words, if you're in here, in the TV plot, you're in the supercooled liquid region, is approximately equal to a specific volume for the saturated liquid at a temperature T, okay? Temperature is what's driving the variation in specific volume, not pressure. Liquids are highly incompressible. You can jack up the pressure and not squeeze a liquid down much. But you can heat it up and a liquid will expand and contract a lot. So we're saying that the temperature dependence is much more important than the pressure dependence on specific volume for a supercooled liquid. So we can approximate specific volume for a supercooled liquid as that of a saturated liquid. Same thing is true for internal energy. We can say that the internal energy for a supercooled liquid at some temperature and pressure is also approximately equal to U of the saturated liquid at that temperature, okay? So I put a little box around this too, all right? Now, one last thing before we move on, we can't quite say the same thing for enthalpy. Remember we introduced enthalpy last time? Enthalpy is U plus PV. So enthalpy is U plus PV. So H is internal energy plus pressure times volume, or if you like, specific enthalpy is specific internal energy plus pressure times specific volume. Now we got to be a little bit careful when we're evaluating enthalpy of a supercooled liquid because we actually have pressure in the expression. So that guy's variation is not negligible with respect to pressure. Pressure is an important input to enthalpy, so we can't neglect pressure variations when we calculate enthalpy of a supercooled liquid. So let's figure out how we get H for a supercooled liquid. Well, H, supercooled liquid, evaluated at some temperature and pressure. How are we going to approximate it? Let me write out what enthalpy is again. So that's internal energy, specific internal energy, plus pressure times specific volume. And this is for supercooled liquid evaluated at some temperature and pressure, okay? Now let's use our approximations that we have for specific internal energy and specific volume. Specific volume for a supercooled liquid, approximated as that for the saturated liquid, and specific internal energy for a supercooled liquid at any temperature and pressure is approximated as that for the saturated liquid at the temperature. So let's apply these approximations here. Well, this is approximately equal to U for the saturated liquid evaluated at temperature T. That takes care of the first term. Plus pressure times specific volume of the saturated liquid evaluated at temperature T. So we're using the approximation on the product between pressure and specific volume, okay? So these two terms I'm using the approximation for. The pressure needs to be there, We need to leave the pressure term in there and the pressure in that product. Because depending on the pressure, if it's very high pressure, then enthalpy can be much higher than internal energy if the pressure is cranked up too high. So let me write that expression down here. H for a supercooled liquid evaluated at any temperature and pressure is approximately equal to specific internal energy for the saturated liquid evaluated at temperature T plus pressure times specific volume for the saturated liquid at temperature T. Okay, put a little box around this. Put a little box around that. Okay, so you should have 3 boxed expressions now so that you can calculate internal energy, specific volume, and enthalpy for a supercooled liquid. Let's do an example. Let's do an example. It's a lot of stuff. Let's do an example. Let's see here. I'll tell you what, I think I am going to, let's cut it. Okay, let's say we have a container here, schematic. We have a container here. Of a container of water at a temperature of 77 degrees C and a pressure, let's see here, what's my pressure? Pressure of 100 bar. Pressure equals 100 bar. So given H2O at a temperature of 77 degrees C and a pressure of 100 bar. 1 atmosphere is about 1 bar. Remember, a bar is a 10 to the 5th Pascal. So 1 bar is an atmosphere approximately. 1.01 bar is an atmosphere. So this is about 100 atmospheres. It's a lot. Very high pressure. Okay? So we have H2O, 77 degrees C, and at a pressure of 100 bar. What are we supposed to find? Oh, how much H2O do we have? We have 2 kilograms of the stuff. So mass is equal to 2 kilograms. Okay, what are we supposed to find? Let's find the specific, let's find the volume of the H2O, the internal energy of the H2O, and the enthalpy of the H2O. Let's find these 3 properties of the H2O, okay? Okay, so first of all, let's figure out where we are, what the state is. Let's figure out what the state is. Always a good idea, necessary to figure out what the state is so we can figure out what tables to use or how to approximate quantities. So, analysis. So here is our TV plot. Let's just do the TV plot. So here's our dome. Okay, there's our dome right there. And let me put in the 100 bar isobar. 100 bar, okay? 100 bar isobar. Now, let's look at the saturation temperature, the boiling temperature for H2O at 100 atmospheres or 100 bar, approximately 100 atmospheres. Let's see if we can find a Tsat here. Let's see here, share. There we go. So let's look at pressure tables. Here we go, 100 bar, 311.1 degrees C. That's the boiling temperature at 100 atmospheres or 100 bar. So Tsat at 100 bar is 311 degrees C. So let me turn this off. 311 degrees C, that's Tsat. So here's 311, Tsat 311 degrees C, okay? Now we're all the way down here at 77 degrees C, okay? So this is our state right there. We're at 100 bar, we're on that isobar somewhere. We're on this isobar somewhere, and we're at 77 degrees C. So T is less than Tsat. So this implies supercooled liquid. Okay, so that's our state, supercooled liquid. Supercooled liquid. Okay, let's proceed. Let's proceed here. I want to find the I want to find the volume of my container of H2O, supercooled liquid H2O. So volume will be equal to the mass of the H2O times the specific volume of a supercooled liquid evaluated at 77 degrees and 100 bar, okay? If I know the specific volume for my supercooled liquid, multiply it by the mass, then I will get the volume of the liquid. Now let's use our approximation here. So this is approximately equal to, looking back at R, and I've condensed the approximations up here. Specific volume for a supercooled liquid at any temperature and pressure is approximately equal to that for the saturated liquid at the temperature. So this is approximately equal to the mass times the specific volume of the saturated liquid at T equals 77 degrees C, okay? Okay? Now let's see if we can find in a temperature table 77 degrees C. Let's see what we can find in our temperature tables. Okay, that's pressure table, temperature table, saturation temperature tables. I do not have 77 degrees. I've got 70 and I've got 80. That means we're going to interpolate between these two. Here's our specific volume for the saturated liquid at 70 and 80. So specific volume is going to be somewhere close to 1.027. So there's 0.022. 0.027, we're closer to 80 degrees than 70 degrees. So 1.027 times 10 to the minus 3 cubic meters per kilogram is probably the approximate specific volume. Let's get the exact interpolated specific volume by using some kind of linear interpolation. Let's linearly interpolate between these 2 points. Let me show you how this is going to work. So specific volume, here's temperature, here's specific volume. As temperature goes up, liquids expand. So there's some kind of a relationship like that between specific volume and temperature. Now let's put a couple of data points in. Our tables give specific volume at 70 degrees and 80 degrees. In fact, let's look those up again. Let's see here, 70 degrees, 1.0228, 1.0228, 10 to the minus 3. We put the unit in here, cubic meters per kilogram. And then at 80 degrees, it is 1.029. 1.029, 10 to the minus 3. Okay, 1.029. Forget the 1, okay? So those are our relevant quantities. Whoops. Okay, so 70 and 80 degrees, we have specific volume at 70 and at 80. And as specific volume goes up, when temperature goes up, okay, there's some sort of relationship between specific volume and temperature. Now we want specific volume at 77 degrees C, okay, 77. We want to know what this is. Specific volume of the saturated liquid at 77 degrees C, okay? We want to know what that is. Now, what we're going to do is we're going to put a linear connecting line between these 2 points. Assume this is a straight line. And we're going to calculate the specific volume based on that straight line interpolation. So how's this going to work? Specific volume for the saturated liquid at 77 degrees C, approximately equal to, I'm going to take this as my origin for my interpolation. So V sat liquid at 70 degrees C. So this is where I'm going to start. And then I'm going to move from this point out here. Okay? So V sat liquid plus delta specific volume over delta T. So that's the slope of this straight line, times 77 degrees minus 70. The rise over the run on the chart and how far we're moving away from our origin data point. 77 minus 70 degrees, okay? Now, what's the delta V over delta T? Let's see, delta V over delta T. That's going to be equal to specific volume, and I'm not going to write sat liquid, I'm just going to write liquid at 80 degrees C minus specific volume of the saturated liquid at 70 degrees C. The rise, okay, the rise and the run is 80 degrees C minus 70 degrees C, okay? Now let's see if I got some numbers here for you. Let's see here. We have, so 1.0291 minus 1.0228. So this is I guess I'll put the numbers in here. 1.029, I'll leave the 1 out. 10 to the minus 3 minus 1.0228. 10 to the minus 3. And that'll, of course, all have units of cubic meters per kilogram. Don't have enough room for the unit there. And then I have 10 degrees C, okay? So delta T down below. Let's see here, 1.029 minus 1.0228 divide by 10. And there's a 10 to the minus 3 in there. Okay, and we get something quite small here. So this is, oops, I gotta make sure this is right. 1.029 minus 1.0228. And then we divide that by 10. Okay, so I get 6 times 10 to the 1, 2, 3, 4. So that's 10 to the negative 7. 6.2 10 to the negative 7. And that is cubic meters per kilogram per degree centigrade. Okay, that's what the slope is. So VSAT liquid at 70 degrees, 1.0228, 10 to the minus 3 kilograms per cubic meter, plus the slope, 6.2. I'm gonna take out the 10 to the minus 3 there so everything's in the same unit. 6.2, 10 to the negative 4. The 7 becomes a negative 4 cubic meters, kilogram, and then I have my delta T. This is going to be 7 degrees C. Oops, cubic meter per kilogram degree centigrade. Cubic meter per kilogram degree centigrade, and then I have 7 degrees C. We crank that all out, and we get 1.027. 1.0272 10 to the minus 3 cubic meters per kilogram. Okay? So that is the interpolated, linearly interpolated specific volume at 77 degrees C. 1.0272. Let us plug that in and get our volume. Let's see here. The mass was 2 kilograms. And 1.0272, 10 to the minus 3 cubic meters per kilogram. The kilograms cancel out, and I get cubic meters. Okay? Kilograms cancel out, so I get cubic meters, which is what I want, and I end up with a final volume. Final volume of 2.054 cubic meters. So volume of my supercooled liquid at the temperature and pressure is 2.054 cubic meters. So let's put a box around it, okay? 2 cubic meters. Oh, sorry. I was like, God, that's huge. 10 to the minus 3. 10 to the minus 3. Don't lose it. That's much better. 10 to the minus 3. This is about 10 to the minus 3 cubic meters is a liter. So this is about 2 liters or half a gallon. That's much better. So volume 2.054. 10 to the minus 3 cubic meters, or if you like, 2.054 liters. And there's about 4 1/4 liters in a gallon. So that's about half a gallon or so. Okay? All right. Let's calculate internal energy. Let's calculate internal energy. U let's move over here now. U at the temperature and pressure. Well, U, let's see, so that's going to be the mass of the H2O times the specific internal energy of the supercooled liquid. Evaluated at 77 degrees C and a pressure of 100 bar. Okay? And that's approximately equal to, using the approximation, the mass of the H2O times U of the saturated liquid evaluated at 77 degrees C. Okay, so there's the approximation right there. Now, if we go through the same process, instead of having specific volume here, I linearly interpolate for internal energy. So let's go to the tables here. So specific volume, specific internal energy of the saturated liquid. So now I can interpolate between these two specific internal energies. Looks to me like we're going to be about, so 77 degrees is closer to 80. So just eyeballing it, it looks to me like we're going to have like 320 or 325 kilojoules per kilogram, just eyeballing it. So we can do the same interpolation. We can do the same interpolation that we did for a specific volume. Same exact kind of interpolation. And I can get U for the saturated liquid at 77 degrees. Okay, so kind of running out of space here. So let's see here. If you do the interpolation, you'll find that this is 322.29 kilojoules per kilogram. And this is from interpolation. Interpolation, okay? Using the tables. Using the tables. Okay, so I got 2 kilograms of the stuff. 322.29 kilojoule per kilogram. And I end up with 644.6 kilojoules. Running out of space. U equals 644.6 kilojoules, okay? And we're interpolating internal energy instead of specific volume, okay? The procedure is exactly the same. Take the specific volume at 80 degrees and 70 degrees, I'm sorry, internal energy at 70 and 80, and interpolate between those two data points, okay? Using a linear interpolation. So that's U. What about H? What about H? Well, we're going to need the specific enthalpy of the supercooled liquid, so we can use this equation here. It's approximately equal to that of the saturated liquid plus pressure times the specific volume of the saturated liquid. So let's use that approximation to estimate the enthalpy of our supercooled liquid. So H equals mass times the specific enthalpy. And again, this is a supercooled liquid. At some temperature and pressure, and that's approximately equal to, well, I'll tell you what, let's just leave it at that. I'll plug in just a minute. Let's see here, H of a supercooled liquid. At some temperature and pressure, approximately equal to U of the saturated liquid at the temperature T plus pressure times specific volume of the saturated liquid at temperature T. So there we're using our approximation. Now we got most of this stuff. Let's see here. U of the saturated liquid, specific internal energy of the saturated liquid. Getting a little sloppy here. Specific internal energy of the saturated liquid. So this guy is U sat liquid at 77 degrees C, okay? From interpolation, 322.29 kilojoules per kilogram. 322.29 kilojoules per kilogram. So that's the first term there. Pressure is 100 bar. Okay, 100 bar. And then specific volume of the saturated liquid, 2.0, I'm sorry, did I erase it? I guess it's right here, 1.0272. 1.0272, 10 to the minus 3 cubic meters per kilogram. Okay? Now we got some unit stuff to work on here. This is kilojoules per kilogram, and I got bar, meter cubed per kilogram in this term. I need to convert this into kilojoules. Let's see here. So a joule is a what? A Newton per meter squared. A Newton per meter squared. And a Newton, well, so let's convert out of bar first. So let's see here. Let me convert this into pascals. There are 10 to the 5th Pascal per bar. The bars cancel out right now. There we go. So now we got Pascal meter cubed per kilogram. So a Pascal, we want kilojoules. So a joule is a force, a Newton, over a meter. That gives you a joule, a Newton over a meter. A Pascal is a Newton per meter squared. Okay, that's a Pascal. So that means this whole term here, meter cubed will partially cancel with the meter squared, and I'll have Newton meter per kilogram. So this will cancel with all but one of the meters there. I get a Newton meter per kilogram. Now I need to convert this, and this is a joule. That's a joule per kilogram. Newton meter, joule per kilogram. Okay, I need to convert that into kilojoules. So there is 1 kilojoule per 1,000 joules. And so this will cancel with this, and I'll end up with kilojoules per kilogram. 322.29 kilojoules per kilogram. And then I've got all this stuff. Let's see here. A lot of numbers there. A lot of numbers. Let's see here. Oh boy. Well, I got 100. So 1.0272. So I got 10 to the 2, 10 to the negative 1, 10 to the 4th. Okay? And then now I'm down to 10 to the 1st power. So this is 10 to the 1 kilojoules per kilogram. So I get 10.027 kilojoules per kilogram, and that gives me a final specific enthalpy of 332, I don't think I've rounded here, 0.6. 0.6, that looks about right, kilojoule per kilogram. So that's the specific enthalpy of the supercooled liquid at the temperature and pressure. 2 kilograms, 332 kilojoule per kilogram, and I end up with H of 665 kilojoules. So note the kilograms cancel out. So 365 kilojoules. H equals 665 kilojoules. Okay? All right. Okay, so that's it. We got U, H, and volume. Okay, let's finish off today's lecture by looking at properties of superheated vapor. Properties of superheated vapor. So we got the saturation dome here. Let's put up the TV plot. So let's recall here, we used quality to get properties for saturated mixtures. So inside we have saturated mix, where quality is important. Put in an isobar here. Then over here we have supercooled liquids. Okay, we just did a problem involving supercooled liquids where we have those property approximations for specific volume, internal energy, and enthalpy. And then out here we have superheated vapor. So this side of the dome, out to the right, we have a vapor or superheated vapor. Remember, it's saturated vapor on the right-hand side of the dome, saturated liquid on the left-hand side of the dome, and therefore we're superheated if we're off to the right-hand side of the dome. So how do we get specific volume, internal energy, and enthalpy for superheated vapor? How do we do it? Well, we have to use a bunch of tables. Tables. What kind of tables? Superheated vapor tables. Superheated vapor tables. Let me show you what I'm looking at here. Okay, so here's our saturation temperature table, our saturation pressure table. And if I keep going, table B4, superheated vapor table for H2O. Pressures are listed here. Temperatures are listed here. Specific volume, internal energy, enthalpy. Don't worry about entropy, that's going to come up later. So properties of superheated vapors as a function of pressure in bar and temperature in centigrade. You have pages and pages of superheated vapor tables. All right? So let's do an example here. There's nothing more than looking up properties in a table. So let's set up an example here where we're going to deal with superheated vapors. So let's switch out. Okay, superheated vapors. So let's say we have H2O. So example. This is going to have some superheated vapor stuff in it. Let's say we have given H2O. And we start off at a temperature T1 of 520 degrees C and a pressure P1 of 100 bar. Pretty high pressure, pretty high temperature, okay? And then we have an ISO, I'll tell you what. This H2O is in a rigid container. Rigid container. What do I mean by rigid? I mean constant volume. Constant volume. No change in volume, rigid container. So this H2O starts off at T1 and P1 in a rigid container. Let me put up the schematic. So here's our rigid container. And initially we have a temperature T1 and P1. So this is state 1 right here, okay? So we have H2O in a rigid container. And then we cool the H2O down until we get a temperature T2 of 270 degrees C. Okay? So we got this rigid container, and now we end up at state 2. And we have a temperature T2. All right? What are we supposed to find? Find. Oh, I'm going to run out of space. Find. I want to find the pressure P2. I want to find the final specific volume, V2. And I want to know the state. The state. Is it a supercooled liquid? Is it a saturated mixture? If it's a mixture, what's the quality? Okay, so what's the state, what's the specific volume, and what is the final temperature at state 2? Okay? Now to whet your appetite here, let's put up the TV diagram. We'll finish this up next time. So I've got my P1 isobar. I don't know where I am on the isobar, but I do know it's a rigid container, constant volume. I do know that I'm going to be moving horizontally up and down the TV diagram. Why horizontally? Because if it's a rigid container, it's an isochoric process. We will finish this up next time, and then we will move on to ideal gas law and some additional stuff from chapter 2 in the remaining part of the lecture.